Okay, so started recording. Let's remember what we have done previously. We said that when you are making a downsampling, as long as it's a rectangular or a square excuse me, not downsampling. If you're making a sampling, as long as the sampling grid is a rectangular grid, it makes a simple replication of a central band-limited Fourier shape, and it makes the replicas of those horizontally and vertically with tiling. Now, there exists a problem when the sampling grid is not rectangular. For example, this V that we can see here is T1, 0, T0, 0, T2. So it's a diagonal sampling matrix. And with that sampling matrix, the periodicity, the frequency periodicity that we have will be 2 pi over T1, 0, and 0, 2 pi over T2, which will very easily make replicas of the central shape. And those replicas can be easily extended to a 2 pi periodic case, which corresponds to the discrete time Fourier transform, the last figure that we see. Originally, the replications were 2 pi over T1 by 2 pi over T2, horizontally and vertically tiling. Now they are 2 pi by 2 pi because we know that the discrete time Fourier transform is 2 pi periodic, and the two-dimensional discrete time Fourier transform is 2 pi by 2 pi periodic. Those are the conditions. Now let's think of another situation. So for that, I'm opening a new page where a similar shape band-limited signal, band-limited two-dimensional signal is sampled by this. V is equal to 1, 1, 1 minus 1. Clearly, this is not horizontally and vertically rectangular sort of sampling. It is some sort of a rotated tile. If you want to visualize what kind of a sampling grid it corresponds to, one of them is let me plot them in red. One of them is 1 by 1, which is this. Okay, this is 1 by 1. And the other one is 1 by minus 1, which is this. Okay. So these two vectors will be now tiling. You may notice that after sampling in the continuous space domain, but if you assign the first sample direction and its replicas alongside that direction, there will be a problem when you convert them to discrete time, because those will not be now located at 45-degree alignment along a 45-degree line, and it's lines. They will horizontal action, and the other one to vertical will be sort of smeared. Here it won't be smeared because Sorry, I think the system kicked me out. I'm asking for you to wait. I know why. Just wait. Okay. Sorry for the interruption. So I was saying that the rotation and the symmetry, etc., all of the properties of the image changes if you make a non-rectangular sampling. This is a non-rectangular sampling in the sense that it actually rotates. It is still rectangular, but a rotated rectangular thing. It doesn't even have to be that way. It can be very asymmetric type of lattice periodicity. So things may dramatically change. So when you do a sampling with this one, let's write down the W matrix, which is the periodicity in the frequency domain. What's going to happen in the frequency domain? What kind of periodicity we will have? And that is 2 pi times V inverse. And that is, it makes pi times 1 minus 1 minus 1 minus 1. Or you can also write it as pi minus pi minus pi and minus pi. So this is the periodicity which will create replicas of the original central tile. The easiest that we have is again the diamond shape. So let's start from that diamond shape band limited signal. It's easy, and it also shows in case any rotations or smearing, it's easy to visualize from this kind of a shape. So this is T1 and T2 axis, and I'm drawing the support, the Fourier transform shape of x of T1, T2. But of course, it's in I'm writing the time, but I'm drawing the frequency signal. So it is the Fourier transform of x of T1, T2, as I said. So let me write it that way at least, like capital X of omega 1, omega 2. Omega 2, something like that. It may be even more convenient if we transform everything to uppercase omegas. So I apologize again and convert these to uppercase omega 1 and uppercase omega 2. This is omega 1, this is omega 2. Because now we'll be interested in the final form, the discrete time Fourier transform in the shape of lowercase normal omega 1 and omega 2, like the W letter. All right. So when we multiply this signal with a bed of nails with this kind of a periodicity matrix, how will these omega 1, omega 2 axis diamond shape be replicated? They will become periodic with this one. So let's do it. Here I need relatively larger space for the illustration. This is the central normal thing. Whatever the edges correspond to, you have to be careful about that. If, for example, this is A, this is again A. And inside it, we have the Fourier transform, therefore it's band limited. Now we have to make replicas of this with this periodicity matrix. So the first one will be at pi by minus pi. Where is pi by minus pi? For that, of course, I have to put a grid to pi and minus pi. Let's say that this is pi and this is minus pi. So around pi by minus pi, I have one replica of this, which will perhaps look like this. Okay, the same shape. And the other one is minus pi by minus pi. And minus pi is here. So around here, I will have another replica, which will probably look like this. Very well. And then I need to have linear combinations of the same periodicity matrix. For example, I may have a negative minus pi by minus pi version of the same, which will then appear at pi by pi, which is then here. Okay. So as you see along the 45 degrees format, they are repeating themselves. And along the minus 45 degrees, they are also repeating themselves. They must also repeat themselves. So we have this replica and all the other replicas too. And not only that, these periodicity vectors can be combined, linearly combined. So I can go with 45 degrees and then I can return at minus 45 degrees. And then I come to 2 pi here at this point, which is 2 pi. And around the 2 pi, I will again have the same diamond shape, like this. So this also exists. And around here, I will have this. This will also exist. So I will have another line. I will have another line here too, and something around minus 2 pi, which will look like this. Like this. And they will also extend this way and that way. So we have this kind of a tiling. It's like the tiling that is rotated by 45 degrees. It looks like that. Now this will have to be converted into, by the way, let me indicate that these are still capital omega 1 and capital omega 2. Now we have to convert everything to discrete time, and we have to look at the x of e to the j omega the discrete time Fourier transform. And the discrete time Fourier transform needs to be 2 pi periodic. So what kind of a situation do I have to have if I convert, as I say, all the 45 degree sampled versions in time domain that I indicated with that red arrow with green encirclement. If I make it horizontal, and if I make the other minus 45 degree red arrow as the vertical axis, it essentially corresponds to making this rotated shape to be rotated again in such a way that it becomes rotated and expanded in the dimensions in such a way that everything becomes 2 pi by 2 pi periodic. So I will keep things in red and notice what I'm doing. I'm now creating a new axis of lowercase omega 1 and omega 2. I'm taking the tiling, the black tiling at the top, and I'm rotating it in a way that it makes everything 2 pi by 2 pi periodic. And that makes a shape like this. This is 2 pi. And this must be, again, around 2 pi. And this is 2 pi by 2 pi. So, can you see what happened here? Because a strange thing happened. The perspective way of looking at the tiling has changed. It's not a diamond shape anymore. It became a rotated and expanded version of the diamond, which happens to be a square shape because the expansion at both directions are equal. So it became a square. And yeah, that's the way we make the tiling. The whole central shape now can be visualized like this. So all the other replicas are also like this, as opposed to the tiling that we have in black. Like this. This is a capital X of e to the j omega bar or omega vector. And what's the formula for that, or how can we express that? Well, the formula for it is luckily simpler than visualization of that in your mind. It's x of e to the j omega is equal to 1 over absolute determinant v. But before proceeding, can you tell me if this point that I put with the red dot on the black figure, A point, if that point is A, can you tell me what is this value geometrically? If you rotate and expand it to become 2 pi by 2 pi periodic, what does that correspond to? What is this black point on the red figure? Can you give me your guess? Can you tell me your guess?
It expanded by square root of 2, right?
A times square root of 2, you're trying to say, right?
Yes.
It is expanded by square root of 2. No, yeah, that's correct. So are you suggesting it's A times square root of 2?
No, no.
You're right, it's expanded by square root of 2.
But it's not the same point, right?
It's the same point, exactly. Look at the green point that we have here on the black figure. That point is A over square root of 2 already. Yeah. The distance from the origin to that green point is A over square root of 2. So when we expand it by square root of 2, as you have correctly inspected, this becomes A. Of course, this is just a numerical example. It doesn't have to be like this. And notice that this 1, 1, 1, minus 1 sampling is still something in the easy category, an easy hexagonal type of sampling. And it's a commonly used one still. Now let me continue with the formula x of e to the j omega. If that V matrix is arbitrarily selected, in another way. As long as it is non-singular, you can make a sampling with that, although it will probably be useless sampling. So x of e to the j omega is equal to, for all k, the x analog of v inverse transpose. Let me do it like this. Let's make a cheating here. V inverse transpose times omega minus 2 pi k, where, of course, k is an integer vector. So I'm making these replicas. But in 1D, it was easy. It was omega over capital T. So V inverse transpose times omega was essentially omega over capital T. And that doesn't perturb any alignment because there's only one direction. It is one-dimensional. But in 2 dimensions, if you first take the inverse of this and then multiply it with the omega vector, actually it corresponds to a rotation and a scaling kind of distortion on the previous axis of capital omega. So this as a total corresponds to, as we know, the uppercase omega vector. So there are some rotations and scalings that are happening when you convert everything into the discrete time. By the way, I can also write the same formula this time on the uppercase omega axis, like expressions, again with the same double summation for all k vectors, integer vectors, capital XA omega, yeah, minus 2 pi V inverse transpose times K. And we know that this thing is equal to W, as we said, 2 pi V inverse transpose. It's actually W transpose. It's not W, but W transpose. So this is what we have to be careful about. Now, I want to come back to this black shape, and I want to emphasize something. Now, using this kind of a sampling vector, sampling matrix, sorry, V, 1, 1, 1, minus 1, notice how the tiling of this diagonal shape is made. So let's, for example, reduce this the values inside v, which are 1, 1, 1, and minus 1. Let's scale it with alpha. Let's make it alpha, 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 minus alpha. Okay. Now, the if alpha is smaller than 1, then W will become larger. Okay, it will not be, for example, for alpha is equal to 0.5, then W will be 2 pi minus 2 pi minus 2 pi minus 2 pi. So they will be very much scattered. The scattering will be larger. But if alpha is a larger number, if it is, let's say, 2, then these will not be periodic with pi minus pi and minus pi minus pi, but instead of that, it will be periodic with pi over 2 minus pi over 2, etc. So it will be more closer to one another. So by making that alpha larger, the sampling period, in other words, larger, we can make these pack or tiling closer to one another, and it may converge to a situation like this, and then this. So they are very much near to one another. They are almost touching to one another. And this, and this, etc. If you understand what I'm talking about, they may become very close. These scattered tilings may become close. And when it reaches to this kind of a touching position, as you see, we can have, we are supposed to have no gap. If this is the tiling, of course, or if this is the baseband Fourier transform support. Normally, we don't have diamond shapes, obviously, but we have some kind of a circular symmetry because we don't have any direction sensitivity in real life images. So we can assume that the thing is essentially like a ball, okay, a circle. And when you consider a circular shape, still the most compact way of putting these things will be like this. It will be with this kind of a no gap strategy. Actually, it's not going to be like this. It's going to be something else. It's going to be 60 degrees rotation and smearing. This is 45 degrees. Therefore, this is not hexagonal sampling, but it is a rotated square sampling. Nevertheless, it is more efficient for this region of support. An exam question that you will encounter will consist of this problem. I will give you a shape, a baseband shape. It's not going to be a diamond shape, but it's going to be something else. And with that something else shape, I want you to find the most efficient sampling. The most efficient sampling is the maximum sampling period, okay? The widest separation with which you still have no aliasing. So as long as the shape does not overlap with one another, for example, here, the shape does not overlap. So something like this, you have to apply to the new shape in such a way that you are trying to get rid of the gaps as much as possible, which is in turn maximizing the period, which is in turn maximizing the determinant of V. So that is your motive here, motivation. Maximize the absolute determinant of V for most efficient sampling. That is the widest sampling because we want to have as few samples as possible, which still retains all the continuous time information, because we can always go back to the continuous time as long as you don't have any aliasing. If these things don't overlap, it means there is a way, there's a digital to analog conversion that will ideally reconstruct the continuous time image or two-dimensional signal. So the trick, I think you understand, we are trying to get rid of the gaps as much as possible. For the most efficient sampling of the analog signal. And the shape will be the shape that I will ask in the exam question. You will see, and you will still have a lot of time, but I'm still free to mention about that. It will be a non-convex shape, so there may be extensions like the horns of the Fourier transform shape. It's just a shape, so I'm free to draw it with my hand. And as long as those horns even don't touch to one another while minimizing the empty spaces, you want to make a tiling. So it's like the floor tiling shape that I'm giving to you, and I want you to tile the floor with that floor tiling, and I don't want you to leave empty gaps between the tiles. So how are you going to do that? You're not allowed to rotate in a continuous time Fourier transform. You have to just replicate, and with those replicas, You have to make the best tiling. After the rotation, the best tiling will still be translated as the best tiling because the rotated best tiling is still the best tiling. So you don't do that. You just tile at the original orientation in continuous time Fourier transform. Afterwards, you rotate to make it a discrete time Fourier transform, like we did from this black shape to the red shape. The efficiency between these two shapes, the black and the red shapes, are the same. Okay, so that is the sampling. All right, now I will continue with resampling, that is the downsampling business. It may be a good idea to the shape of the page. But yeah, there it is. No, not this one. No, a denser grid. Yeah, this is good. So now I want to make a downsampling. I think it will be a good idea to write the formula of the downsampling immediately, because we have seen what's happening in the one-dimensional case and we spent a lot of time for that. So we already know what the downsampled version looks like. Now I want you to understand that what I mean when I write it like this is capital Y of e to the j omega bar, but it's too long to write it that way, so that's why I'm writing it like this. This is equal to, if the downsampling matrix is something, let's give a name. Unfortunately, in my notes, I was stuck with my notes, and that's why I'm a little bit worried about that. So the title, let's write the title so that you don't get confused with that, is downsampling. I'm using a V matrix for downsampling, which was the sampling matrix of the continuous time signals too. So should I use a different matrix? Maybe I should. Let me call it M, okay, capital M. Then when I downsample with a matrix like this, it's a downsampling operation by a matrix M, capital M. The downsampled versions discrete time Fourier transform with respect to the discrete time Fourier transform of the not downsampled signal. So the right-hand sided X and the left-hand sided Y are both discrete time signals. We were having 1 over n or something like that if you are downsampling with n, if you may remember. And do you remember that when you downsample, you make, if you are downsampling by 2, you have 2 replicas of the original signal. You remember that? Because when you make it wider, a 2 pi periodic signal becomes 4 pi periodic, wider. So we have to insert something else in between to make it again 2 pi periodic. If we make it if we downsample it by 3, it will be 3 times wider and 2 pi will go to 6 pi. So we need to insert 2 extra components, one for the 2 pi, one for the 4 pi. And everything now becomes 2 pi periodic. So we were adding some additional terms. And how many terms were we adding? It depends on the amount of downsampling. If downsampling is by 2, then we were putting 2 terms. Now we are putting determinant of M many terms. M is the downsampling matrix, and M, by the way, is an element of an integer matrix. So the elements of M cannot be arbitrary. It can't be pi minus pi or something like that. It has to be 1, 0, 0, 2 or something like that. An example, let me immediately give you an example. M is 1, 0, 0, 2. This is a downsampling matrix which applies the downsampling only vertically, and horizontally it's not applying a downsampling. So the height of the image is now half. It was originally, let's say, 100 by 100. Now it is 50 by 100, okay? Because the height is half if you downsample with this downsampling matrix. If you downsample by 2002, it means the new image becomes 50 by 50 because we are downsampling both horizontally and vertically. But how about if I give M is equal to 1, 2, and minus 1, minus 1? What kind of a downsampling is that? It is still a downsampling, and the downsampling or image size reduction will be determined by the determinant of that M, okay? So that's why we are dividing by it, because the energy is reduced this much. And let's say I from 0 to that determinant of M, which is like N, okay? That is the size. We should better find a terminology, a short term for that maybe. And capital X of 1 over M, which is M inverse transpose, omega minus 2 pi Ki. There is something that I haven't mentioned about, and that is Ki. In the previous method, in 1D, so let me open a parenthesis, in 1D, the formula was like this: y of omega is equal to 1 over M, I from 0 to M, x of omega minus 2 pi I over, over M. This was the formula in one dimension. Now the two-dimensional formula is like this. And as you see, we have 2 pi I, because I is an integer, therefore it's just there. We're just multiplying 2 pi with that integer from 0 to M. It's not 0 to M, I'm sorry, I think it's 0 to M minus 1. So this one is also determinant of M minus 1. And this is also M minus 1. Yeah, this is correct. I is, if M is equal to 2, for example, then I is 0 and 1. We have two copies. But now I have to use something different. I have to use these KIs because it's two-dimensional. Okay, this is an integer vector. Ki is an element of a vector. It's an integer vector. And it must be chosen or selected according to the shortest vectors that will make these replicas to span the 2 pi by 2 pi space. And they are called, there's a name to those things, they are called the coset vectors. It's not a very difficult concept to understand, and I'm sure you may take a look at some literature to understand what coset vectors are. The coset vectors, for example, are 0, 0, 1, 0, 0, 1, and 1, 1. If the downsampling determinant size is 4 for this one. So if the, not for this one, it's for for the 2002 case. So the determinant is 4. So the downsampling scale is 4. It means you need 4 coset vectors. The first coset vector is default 0, 0. You don't have to change it. The others are the smallest vectors, which will make the tiling. Let me continue with red with the same example. When you make a downsampling with that one, this original tiling will become 4 pi by 4 pi periodic, like this. Like this. So it is 4 pi by 4 pi periodic. So how can I make it with the downsampling? It becomes like when you divide by m, in other words, it becomes 4 pi by 4 pi periodic. So how am I gonna make it 2 pi by 2 pi periodic? I have to add some extra components. One of them is 0, 0 is itself the red one. Then I will use 1, 0, which is a shift to the right by 1. And that 1 ki is equal to 1, 0 is multiplied by 2 pi, because there is 2 pi k sub I in the formula, as you see, 2 pi times k sub I. So it will be shifted to the right by 2 pi, and it's going to contribute these 2 pi periodicities alongside, like this, these black ones. But that's not enough. These red shapes must be replicated more. For example, for 0, 1, let me use the blue color, maybe even a lighter blue, like this, which corresponds to this time vertical replicas, which are these. So the red shapes are vertically repeated, and that makes those things to be having a 2 pi periodicity, some of them. So I'm one by one, as you see, stacking the tile. Let me bring it here. And now let me put the green, which is 1 by 1. That would make a 2 pi by 2 pi replicas of the red shape, which corresponds to the diagonal replicas, which are here, the greens, like this. Now, as you see, everything became 2 pi by 2 pi periodic. So the red one is the red one. 1 by 0 is actually the black one, so maybe I should write it like this, 1 by 0. And 0, 1 is the blue one, and 1, 1 is the green, sorry, the green one. So these coset vectors, therefore, in short, are supposed to be inspected or selected according to tiling the shape to become 2 pi by 2 pi periodic. Because when you make the downsampling, when you divide by m or multiply by m inverse transpose, when you multiply omega by here, when you multiply omega by m inverse transpose, without those replicas and without that summation to the left of it, it will be scattered too much. It won't be 2 pi by 2 pi periodic. It will be another tiling. But we know that the discrete time Fourier transform is 2 pi by 2 pi periodic. So we have to insert, substitute those missing components. So this is, in short, the downsampling phenomenon that we have been looking for. There are other examples you may think of. For example, V, it's not V, we didn't call it V, we call it M, right? M is equal to 2, 1, 2, minus 1. Now the determinant, the absolute determinant of M for this one is minus 2, minus 2, minus 4, absolute value is 4. Interestingly, as you see, this one also causes the signal to become 1/4 of the original size. But it's a different one. Or this M, which is 2, 2, 2, 0. Again, the determinant of M is still 4 for this one. So this also makes the signal to become 1/4 of the original one. But those 1/4 in the area, in the size, are not the same, because some of them are smearing a little bit and then making it narrower or distorted. Some of them are more symmetric. The original one that we did in this example that we tiled is the easiest downsampling, 2002, because it is rectangular downsampling, and it didn't change the shape of these diamonds. They become wider, equally wider horizontally and vertically. Therefore, it's still the diamond shape that we have after downsampling. In downsampling, since these diamond shapes or whatever shapes are also becoming wider and larger, and the other one, replica around 2 pi, will also become larger, and they may start overlapping. So there may be a problem of aliasing, and in order to avoid that, you have to apply an anti-aliasing low-pass filter to be on the safe side before downsampling. You just cannot downsample the signal. As I gave an example in the previous week, if it is a checkerboard, for example, when you downsample with a hexagonal downsampling tiling factor, it will become completely black or completely white. And that's because of aliasing. Now, what time is it? It's it's 20 past 10. I will write 2 questions, okay? And then afterwards we can give some longer break. I will write 2 questions, and those 2 questions are essentially your take-home exam questions for this midterm. I will also write them in the form of a formal question, and I will submit them to you. But now I'm explaining the question, so you may want to listen to those things. Okay. It's a take-home exam question. So, question is as follows. Suppose that we have a downsampling matrix and V is a sampling matrix. Actually, I asked this question before for the one-dimensional case, but in your midterm, the question will be in the form of a two-dimensional format. So you may want to become more familiar with this one. We sample XA of T with this sampling matrix V to make its first XA of V times T, let me put it like that, which in turn is converted to X of N. What is happening? x of n. Now, from here, I take x of n and downsample it with m to obtain a signal. Let's give a name to that signal. Let's call it y of n. Okay, this is y of n. Now I take the same x sub a of t and sample it with m times v to obtain y a of m times v times t, and then I convert it to the discrete time y of n. And I want you to show that these two things are equal to one another. In other words, if you first sample your analog signal and then downsample it, it is equal to immediately sampling it with a different sampling matrix that incorporates both the sampling and the downsampling. So if your sampling is m times v, then it actually makes the downsampling beforehand. It is quite trivial and it's very obvious to see it in time domain, but I want you to show this to prove equality in frequency domain. You know the formula for downsampling. Where was it? Let's go back. It's here. This is the downsampling formula. So first apply the sampling formula and then the downsampling formula and come up with an expression. And later on, apply the sampling directly with m times v matrix and come up with the expression. Can you verify that? Can you verify this equality, which will be a proof of what we have done so far? Okay, this is one exam question that I want to ask you. It's more like, it's not really a question, it's more like an exercise. You do some mathematical writing exercise. This is equal to that, therefore this is equal to that. With no assumptions, of course. I want you to make a rigorous proof of this thing, which may give you some ideas about how to choose the coset vectors and things like that. So it will be an inspiring example or analytical exercise for you. The other exercise question that I want to ask is a longer one. It's like this. You have a discrete time signal. You are already starting with a discrete time signal that has been sampled to become like this. 2 pi by 2 pi periodic, of course, because it's a discrete time Fourier transform of an image. So this is 2 pi, similarly there. And these points are numerically given to you. These are pi over 4 and pi over 4 and minus pi over 4 and minus pi over 4, all right? So this diamond shape is already given like this over the lowercase omega 1, omega 2 axis. So it's a given signal. Let's call this x of omega, corresponding to the time signal x of n. step one, or part A of the question is, you downsample this x of n, downsample with a v. This v is not sampling, so don't get confused about that. Maybe in the exam question, I may prepare it to become m. This is the downsampling matrix I'm talking about. We are downsampling it with v to come up with x1 of n. And this v is given numerically. It is given as 3, 1, and 0, 2. Notice that the determinant of this downsampling matrix is 6. That complicates things a little bit, and that stretches the size of the question. The question becomes very big. Because it is downsampled by 6, it means that these diamond shapes are scattered all around in such a way that you have to find 5 additional coset vectors. This one itself will be, or its wider version will be the 0th coset vector, and you need 5 more, a total of 6 coset vectors. I want you to do this on the tiling on a large grid paper. So just buy some grid papers, or you may tear off some of the pages of your notebooks, grid notebooks if you have, and show them on the grid. And I want you to write or to plot these coset vectors or the coset extensions in different colors, as I did in my previous example. It may be difficult to find 6 different colors, so you may use dashed drawings and things like that. You may need a lot of pencils for this question. And I want you to draw x1 of omega by indicating cosets with different colors. Different colors would be good. Of course, you have to eventually take the photo of this and send them by email, make a PDF and submit the exam by email. Now, there is a further problem that we didn't exercise. So in this question, it's going to be you to exercise for that. Where I have to go to the previous page. Look at the formula in this part. The others are the coset vectors, 2 pi repetitions. But when you take a look at the blue encapsulated part, it is m inverse transpose times omega. That also disturbs the shape. If m is 2 by 0, 0 by 2, then m inverse is 1 over 2 by 0 and 0 by 1 over 2. It's fine. And it's very easy to multiply it with omega. But if it is not such a rectangular downsampling, where here in the question it's certainly not a rectangular downsampling, it is 3 by 1 and 0 by 2. So it's not rectangular, which means these shapes, these diamond shapes, will not only become larger, but they will also become distorted. So how will you find the distortion? Or it's going to have a new shape now, some kind of rotated, expanded, just distortion. So what is that distortion, and how are you going to find that distortion? Let me answer that question, because if I leave it up to you, you may fall into some problems. This V inverse is something that you have to find. I'm going to write everything in red, which is not part of the question, but it's part of the answer hints for you to follow. V inverse transpose, let's give a name to this. Let's say that it is the A matrix. So that A matrix is now multiplying omega. That way, you may want to see what is the new point which originally corresponds to a point that I already know. What are the original points that we already know? There are 4 landmark points on this shape. They are here, 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 and here. These 4 points. So using this kind of a transformation, it may be wise to see where these points go. If you can find 4 new points that correspond to originally these 4 red points, if you find 4 new points, you just connect those 4 points and that will be your new shape. Okay. If A is, for example, 1 over 2 by 0, 0 by 1 over 2, like this, that makes omega 1 over 2 and omega 2 over 2. Okay, and suppose that in the previous example, let me go back to the previous example. Suppose that the point that we have, which we didn't have, sorry, the original diamond shape is here, and this point is, let's say, A. Okay, this red point is A. Then by omega over 2 equals A, by saying omega over 2 is equal to A, you find the new omega value. What I mean is this point is omega over 2, omega 1 over 2. So for which omega 1 value do we have omega 1 over 2 is equal to A? That makes omega 1 is equal to 2A. That's how you make the inspection. In the new case, therefore, after multiplying with A, you will have some formula relating omega 1, omega 2. It's a function of omega 1 and omega 2. This is also another function. This is F1, this is F2 of omega 1 and omega 2. And you have 4 equations to solve. The first one is, this is equal to pi over 4 by 0. Okay. And then you will find the point of omega, the new omega 1 and omega 2. Find omega 1, omega 2. That will be the point which converts this pi over 4 by 0. Okay, you make this equation. There are 2 unknowns, omega 1 and omega 2, and there are 2 equations, the top and the bottom equation. From there, you solve for omega 1 and omega 2, and that will be the omega 1, omega 2, that where this pi over 4 point, pi over 4 by 0 point will go. Then you will do the same to this 0 by pi over 4. So you are going to write it again. F1 prime omega 1. No, it's not F1 prime, it's the same, F1. F1 omega 1, omega 2. F2 omega 1, omega 2. These functions are line functions, by the way, they are linear functions, is equal to 0 by pi over 4. And then you find omega 1 and omega 2. That's where this green omega 1, omega 2 will go. So these points will go to some different places, and probably they will go to some faraway places because this diamond shape has an area, and the area of the new shape that is formed by the new points, by joining the new points, must be 6 times larger. The area is 6 times larger. So these new points must be going to some faraway places. Where are they going? Be careful about that. Solution of part A requires that knowledge. In fact, solution of the rest of the question will also require that knowledge. In B, for example, part B of the same question, we apply x1 of n to a filter h of n to find x2 of n. What is h of n's Fourier transform? It's an ideal low-pass filter. Therefore, it's also 2 pi by 2 pi periodic, and it is an ideal rectangular low-pass filter, like this. This is 2 pi, like this, and this. Okay. Now, but it's a deterministic low-pass filter. This is pi over 2. This is pi over 2 minus pi over 2 and minus pi over 2. So this is the low-pass filter that we apply to x1, which is the downsampled version. Notice that I told you that x1 is a larger version of x. Therefore, it will be a larger diamond. Originally, this diamond that I indicated from minus pi over 4 to pi over 4 bounding box will be wider. And because of it becoming wider, actually, it may be wider than this pi over 2 range. And this low-pass filter will retain only the portion inside it, and all the tail portions that go beyond this rectangular shape low-pass filter support will be cut off. It will be cut off from the center 0, 0. It will be cut off from the replica at 2 pi horizontally, 2 pi vertically, and 2 pi by 2 pi diagonally. All the replicas will be clipped off. If there are some ears, for example, that protrude or extend beyond these this rectangular box, those ears will be chopped off. Okay, that's what the Fourier transform of x2 of n will look like. And the question is therefore, draw x2 of omega. How do the tail or ear portions be cropped? That is the thing that you are supposed to do. But the question does not end there. Then you, in part C, this time you take this cropped signal and upsample it with, did I say V? Yes. You upsample it with V again, and you come up with x3 of n. Upsampling is simple, but we haven't seen it. So this question, while doing this question, you will have to learn how things go. Upsampling will be very simply the reduction of the repetitions, the spectral replicas of those diamond shapes or distorted diamond shapes. All those distorted diamond shapes will come back to the original position. So it's like x3 of omega will be equal to x2 of V times omega. Very simple. This is the formula. I didn't tell you this formula because we have seen it in one-dimensional case already. In 2 dimensions, it's simply like this. Originally, we were dividing by V, or we were multiplying with V inverse transpose. It was V inverse transpose times omega. Now it is V times omega, and there's no summation or any extra terms. This thing makes everything to become smaller, but while becoming smaller, those 2 pi by 2 pi periodic extensions will now become smaller periodicity. It will eventually also be 2 pi by 2 pi periodic, but the shape that we have originally in the question, this shape, will contain some extra components. Or those extra there are 5 more extra components that are fitting inside this tile. And by the way, the shape will be transformed back to the diamond. While expanding, it was distorted, and replicas are there. While squeezing back everything, it comes back to the diamond shape. And all the extra terms will also come back to the diamond shape, except they will be cut from the ears and tails through this filter, low pass filter. So it will be maybe some cropped versions of this diamond shape. Maybe, I don't know. You have to be careful with these drawings. And I want you to draw x3 of omega with the same color labels that you used in the cosets, because when you shrink them down, those coset vectors will still have the same color. So please draw this thing, x3 of omega, again with the same colors that you use for drawing x1 of omega. So we have therefore a 3-way process: 1 downsampling, 1 filtering, and 1 upsampling. And I want you to draw the outcomes of all these things. And it's not easy. Yeah, and it's cumbersome. It is, of course, not very difficult. There's no complication. This is an obvious question. But in order to solve this obvious question, you have to be careful with how they are rotated, where they are cut, and after cutting, when they rotate back to the original diamond, how do those cut portions be shrinking to the upsampling shape, etc. It's a cumbersome question, but it's a very good exercise for you to follow, and you will have a lot of time to solve it. You can even start solving this question, because that is clearly the question that I will ask. And I'm not going to change the coefficients. It's going to be 3, 1, 0, 2. Because if you do it with this one, and if I ask with some other coefficients, it would be a misery for you to solve this question, and then you come up with a different set of numbers, which will just spoil all the solutions, and you have to solve it again for the new terms. I'm not going to do that. I'm going to ask with the same numbers. So start solving this question. And this also, these 2 questions also finishes the concept of sampling. Sampling is particularly important for efficiency. Nowadays, in image processing, with modern computers, people just don't care about that kind of efficiency. The number of pixels, let's make it larger and larger and larger. They don't care how much space they are occupying. Or they may do some further compression after sampling. So while sampling, efficient sampling is an issue. In fact, there is a further research idea that is generated from here, which is still an open research topic. So you may be researching for that as your project, which you have to decide, as you may remember, which is called sparse sampling. In sparse sampling, it is not even a periodic kind of sampling, but it is just a sampling bed of nails, irregular bed of nails, which samples densely at high frequency ranges and sparsely at lower frequency ranges in such a way that, so it's a non-uniform sampling, it may be, such that with that sparse sampling, the signal can still be reconstructed. It's not really a topic of normal image processing, but in signal processing that requires acquisition of the sample to be as few as possible. For example, in military range scanning and things like that, we don't want to just make measurements or take measurements a lot of times in military, because then the enemy will notice you and he will fire at you. So we don't want to do that. We want to take as minimal measurements as possible. There are other applications too, where the idea is still this kind of an efficiency, which maximizes the sampling efficiency or the sampling density. Okay, it maximizes the density of the sampling. But that's all for this course regarding image processing. So this finishes the chapter regarding sampling. If you have any questions, you may ask now, or you may start solving the questions first, and then you may come up with some questions, and you may ask them by email, you may consult me. Or if you have questions now, you can ask. Otherwise, we can now give a break until 10 past 11. Okay. 10 past 11. So I don't see any questions in raising hands, any comments. So I'm stopping the recording at this point. We will continue at 10 past 11.